All right. So, hi everyone. Welcome to the Growth Index School. Here we are with the continuation to our last lecture, K theory of monoidal categories. And here we are going to see leftover details on the K theory of monoidal categories. The speaker is also going to talk about Quillen's theorem A and B and its application to K theory. So let us begin. Over to you, Professor.
Yeah, thank you. Before I start, I can see in the audience. So there's Nina Gupta. Nina is in the audience. Is this from ISI? Hello. Okay. Anyway, maybe not. Anyway, so I'll just get to the talk. So let me recall. Okay, first of all, I should
Can you hide
say.
this black box from your screen?
Oh, sorry.
And also turn on your video.
1 second.
All right.
Sorry, 1 second. So my video is not very okay. Is that okay?
Yeah, it's fine.
Okay. So yeah, let me recall what we did in the previous talk. Okay, yeah. Before that, the first of all, I think, I mean, the abstract said a few things, but as I prepared, I realized I may not be able to do some of the things that I have said there. So let's see how far we get. And there is a chance that this may spill over again. So again, we'll see how that goes. The other thing I wanted to say was that I made a mistake in the previous talk. I think there was a question about whether BGL is locally compact. And I said the answer is yes. So I have to take that back. So the answer is no. If if one takes the finite situation BGLN, then it is locally compact. But if you take the limit, then it's not. In any case, that doesn't like seriously alter many things. The point that I wanted to make about locally compact in the previous talk was that uh, uh, so usually when you do CW complexes, etc., you restrict yourself to a category of locally compact Hausdorff spaces, and then so okay, I should be careful. Basically, when you do CW complexes, you change your definition of product in that category, because otherwise the natural sort of product does not reflect the CW structure. So and then you just work along with that. So that works fine. Only thing is when you want to talk about homotopy, uh, there is already a notion outside the CW world. So that should match with the CW world, and that's what I was trying to say last time. Okay, so even if something is not locally compact, that does not alter the sort of way things work, because you can do products in the category of CW complexes. They don't match with the usual product topology, but that's okay. It works for whatever purpose it's required. Okay, so with this brief sort of and rather vague set of statements, I'll again reiterate that BGL is not locally compact. Okay, so what I said last time is not correct. Okay, so I don't know if the person who asked this question is there, but if not, if someone could convey it to them, that will be great. Fine. So let's get down to what we did in the previous talk. So we studied the K theory of monoidal I mean, at the end, basically, I could define the K theory of monoidal categories. And so we defined symmetric monoidal categories. So that's all this data. S tensor 1, A for associativity, lambda for left unitar, mu for right unitar, and then this R which reflects the symmetric nature. So there were lots of diagrams that had to commute, etc. But the upshot of it was that up to certain isomorphisms, you can just get rid of the brackets and flip over your tensors as you want, right? That was the main point of all those diagrams. Then we talked about functors of symmetric monoidal categories. So there were three kinds of functors that showed up. Lax functors, which is a functor on, so F is a functor on the underlying categories, and then epsilon and mu are whatever relate the products on both sides and the units on both sides, the one on both sides. And we don't assume that they are isomorphisms. When you do strong monoidal functors, you do assume that this epsilon and mu do give you isomorphisms. And then strict monoidal functors is actually equalities. So that's that. Then we talked about cofinality of a subcategory with the idea that we'll at some point state the cofinality theorem in this context. Then we took a detour to talk about classifying spaces. And then we recalled that functors give continuous maps, natural transformations give homotopies, and then using that we get that adjoint functors give homotopy equivalences. And as a result, if initial or final objects exist, then the space itself is contractible. The classifying space is contractible. Okay. Then finally, we looked at the S inverse S construction, which was sort of the main point of last time's talk. So I'll recall what this category is. So S is a symmetric monoidal category, and the objects of S inverse S are pairs M comma N, where they belong to the objects of S. And yeah, and the morphisms are equivalence classes of pairs of this form, where S, this beginning S is it's an object of S, and these two are morphisms after tensoring the left guy with S. So F1 is a morphism from S tensor M1 to N1, and F2 is a morphism from S tensor M2 to N2. So somehow we want to think of this as some kind of an action of S, and we want to uh, relate that action in some way. So anyway, this is the definition. Um, so, and then we said when two such things are equivalent, namely when you have if you have S F1 F2 and S prime F1 prime F2 prime, then you should have an isomorphism from S to S prime, which makes the relevant diagrams commute. Okay, so that was the definition. Okay, I have it here. So they are said to be equivalent if this diagram commutes. So S tensor Mi to S prime tensor Mi via this isomorphism tensored with Mi, and then you have maps to Ni, and this thing should commute. Okay, so here's a couple of things, some of which I stated, some of which I couldn't at the end. So the first is that if S is a symmetric monoidal category, then so is S inverse S. So I think this was kind of obvious from what I said, but I think I didn't explicitly state this. So what is the structure on this? So if you have M1 comma M2 and N1 comma N2, then the product structure is you just tensor them, you do the operations um, on each coordinate, right? And then if you have maps, so if you have S F1 F2 and T G1 G2, where does this go? This also goes coordinate wise. So it goes to S tensor T comma, and I need a bracket here, F1 tensor F2 and sorry, this should be F1 tensor G1 and F2 tensor G2. F1 tensor G1, F2 tensor G2. Right. So it goes to this, and then you have to check it's a functor, etc. Now there are other things also involved here like associativity, etc. So that I'm not checking. As I said last time, all those follow. And then what is the unit? The unit is still 1 comma 1, right? So these are pairs. So you have to give two things. So it's 1 comma 1. Okay. And now there are various functors from S to S inverses. And this is really the point, that there are many of them, and we are going to use all of them in order to sort of sort of get to the punchline. So I said this very fast last time, so I want to repeat this. So there are strict monoidal functors F1 and F2 from S to S inverse S. So the first one puts this S in the first coordinate and it keeps 1 in the second coordinate. And the second one puts M in the, meaning S in the second coordinate, and it keeps 1 in the first coordinate. And then you have to also talk about what happens to maps. So for maps, remember that what you want here is an object, um, an object of S. So any morphism in S inverse S is like an object in S and along with two maps. So this is the object. The object is just one, and then you want a map from one tensor M to the like if M is from M to N, then you want one tensor M to N. So that's just the map. I'm just calling it F because one tensor M to M, there is a natural map that's using the left uniter. So that's lambda M. And then the other map, this map rho one, this is from one tensor one to 1. So that's row 1. Okay. And similarly, you have the same thing happening on this side. You have 1, but now the roles of F and row are flipped over, right? So these give you strict monoidal functors. And sort of what I said last time was that if you think of this tensor, this operation as S acting on S, right? This is one way of thinking of this map tensor. That is, S is acting on S, which is to say that if you take an object S of S, then there is a natural morphism it induces from S to S, namely you tensor with this S. So M goes to S tensor M, that's for objects, and F goes to S tensor F, that's for morphisms. So so this gives you a functor, and you can sort of extend this action to S acting on S inverses. Yeah, so you kind of view now in some sense S inverses as something, a category on which S is acting, and we are going to see much more of this ahead. So how do we do this? So first of all, when I say extends, I have to say extends in what sense? Because how is S related to S inverses, right? So because we had two possible functors, F1 and F2. So if you have F1, then the way this action extends is by remember in F1 the S component, meaning the category capital S sort of goes to the first component of S inverses. So here you only tensor the first components of um, the first components by this little s, and if you want to extend it via F2, then you do it on the second components, right? And all the other things remain the same in the morphisms. So you have to check, of course, that this is indeed a genuine functor, both of these. So if I call this G1, if I call this G2, then G1 and G2 are indeed functors from S cross S inverse S to S inverse S. So that's a check. And the main point is the following, that, oh, okay, sorry, I should have been careful. G1 and G2 are not the functors. G1 is a functor induced by looking at the object little s. And G2 is the functor from S inverse S to S inverse S induced by fixing an object little s, right? So in this sense, it extends the action that little s has on capital S, but through the two different functors, F1 and F2. So these two functors are functors from G1 and G2 are functors from S inverse S to S inverse S. And these are like the action of little s. And the main point is that these two functors are homotopy inverses of each other. So which means that if you look at BG1 composed BG2, that's homotopic to the identity, and BG2 composed BG1, that's again homotopic to the identity. When you go to the classifying spaces, right? So this is, so in some sense, S has now, I mean, the action of S is now inverted when you go to S inverses. And that's why we think of this as a, you know, when we had our good old monoids, this was like you attach inverses, right? So here you are not attaching inverses in that sense. It's more like you are taking the action of S and you are saying, I'm inverting that action when you go to S inverses. And inverting in the sense that when I go to the classifying space, it gives you a homotopy equivalence. Okay, so this is the main sort of this is the sort of point behind the category S inverses. Okay, so we can have, there's a more general notion of this of S acting on some category C, and this is crucially used in fact in all the proofs that are going to come ahead. So we will study this a little bit further. Okay, so I hope yeah, I had said all this in the previous talk, but I went over it rather fast at the end. So in case there's questions, please ask me. Okay, so now we want to look at the special case where S is S iso. So what do I mean by that? That means it contains only isomorphisms, right? The only morphisms in S are isomorphisms. For whatever reason, this is the setup that we are actually going to use when we apply this construction for various purposes. So under this assumption, we defined the K theory of S, the K groups of S, as you take the classifying space of S inverse S and then you take its homotopy groups. So this was the definition of the K theory. And of course, now we have many competing definitions. So it's we have to reconcile those definitions. In particular, we defined K naught by hand, right? So here, if we look at K naught of S, well, I can think S is a symmetric monoidal category. So if I just get rid of all the other data and I concentrate on just the objects, forget the morphisms, right? So if I just look at the objects, then that forms a monoid in the usual sense that was in Professor Kuber's talks. And so we can talk about K naught of that monoid. So we should compare those two. So for that, first note that K naught of S as defined here, meaning as pi naught of B S inverse S. So first note that this is a group. So let's first check that. Okay, so what is the operation of this group? So the operation is coming from the operation on the category. So that's M1, M2 tensored N1, N2 is M1 tensored N1, M2 tensored N2. So I'll just remind you that when you do pi naught, that means you're taking connected components of BS inverse S. So so it's, of course, one has to check, of course, that connected components behave well under this operation. So all that is built into the definition of BS inverses. So it just follows from there. Okay, so this is the operation, and then the identity is 1 comma 1. And what is the inverse? This is really the main point. So this inverse is related to that previous fact that I stated, that if you operate by S, if you take the action of S, then that's like creating homotopy inverses. Yeah, by those two functors. This is related to that. So first of all, note that there is always a morphism from 1 comma 1 to S comma S. How? So remember that morphisms are, so this is in S inverses. Yeah, this is a morphism in S inverses. So how are morphisms given? So you have an object. So you take the object little s, and you have maps now. Maps from where to where? So these should be maps from S tensored 1 to S, and for the second component again S tensored 1 to S. Well, of course, we know there are maps like this, right? These are the left or right uniters, whichever, depending on which. Yeah, this is the right uniter corresponding to S. So the maps here are rho S comma rho S. So that gives you a morphism from 1 comma 1 to S comma S. So once you have a morphism, that tells us that the points corresponding to 1 comma 1 and S comma S, they belong to the same component, right? When you think of BS inverses. So in pi naught BS inverses, 1 comma 1 and S comma S are in the same component. So now remember, this is a group though. So I mean, I want to prove it's a group. I already know it's a monoid. There's an operation. So if I can show that if I take some element and I tensor it with some other element, and I get that it's of the form S comma S, then that's really the same as 1 comma 1 in pi naught. And then it's easy to do, because this is a symmetric, we have assumed symmetric. This is a symmetric monoidal category. So if you take m comma n, tensor n comma m, then this is just m tensor n comma n tensor m. But these are the same, yeah, up to some natural isomorphism, etc. So this is really the same as far as the connected component is concerned. M tensor n comma n tensor m is in the same component as 1 comma 1. So in pi naught, it's the same element. And therefore, everything has, each component has an inverse. Yeah, which is just flipping it over. So that's n comma m. And this is very reminiscent of what happened in when we did it monoids to begin with, where when you went to the Grothendieck group, everything could be written as class of m minus class of n. And then the inverse is, of course, class of n minus class of m. And really, this is a proof that pi naught of BS inverse S is indeed isomorphic to K naught S comma tensor, where this is thought of in the sense of a monoid in as we saw in Professor Kubay's lectures. So let's go through a proof very quickly. So if you have S, so now here S is being thought of as a monoid. Just look at the objects with the tensor operation. So there is a map from that monoid to pi naught B S inverses. What is the map? So if you take an object M, an element M, then you map it to M comma 1. But not just M comma 1, you since here you are looking at connected components. So you look at the connected component corresponding to uh, the point corresponding to the object M comma 1 in S inverses. Okay, so now this induces a monoid morphism. This is very clear, because if you have M tensor n, then that goes to M tensor n comma 1. But the operation we know is M comma 1 tensored n comma 1 is M tensor n comma 1. Well, comma 1 tensor 1, but 1 tensor 1 is 1. So this is a monoid morphism. And as a result, it factors through K naught. So where, what do I mean by k0 here? This is k0 in the sense of monoids like Professor Kuber had defined. Okay, so now we get a monoid, we get a group homomorphism from k0 s comma tensor to pi naught b s inverse s. And what does this do? So in terms of the notation that Professor Kuber used, I think it was m minus n. So since here we are using, it was additive notation maybe, or typically that's what's used. Since here we are using multiplicative notation here, tensor notation here, that element is the same as the element m tensored with class of m tensored with class of n inverse. And where does this go? By definition, this goes to the component corresponding to m comma 1 tensored with the inverse of the component tensor corresponding to n comma 1. But we just saw what is the inverse, because pi naught b inverse b s inverse s was a group. So here the inverse of this is this guy 1 comma n, and then you just tensor and you get m comma n. So that is the map. And now it's a very straightforward check that the reverse thing is also a well-defined group homomorphism, and that will complete the proof that this is an isomorphism of groups. So again, I sped through this proof in the previous talks. I thought I should do this again. Okay, so now let me get to something new. Okay, so let's look at categories and classifying spaces. So before doing anything else, we really need to understand this classifying space construction and some results on that called uh, Quillen's theorems A and B. So I just sorry, yeah. Yeah, so let's get back to uh, classifying spaces and categories. Okay, so unfortunately, as we know, once we do category theory, there's a lot of definitions and sort of diagram chasing. So again, can't be help. Okay, so suppose you have a functor from the category C to the category D, something like this, and I have an object of D. Okay, so the comma category F. So unfortunately, it's called F comma D, I think, but it's denoted by this backslash. So the comma category F. So I'll just call it comma. So F comma D. So this is F comma D. So this has the following definition. So the objects are pairs, C comma F, and what kind of pairs are these? This F is a morphism from the functor F applied to C to D. So they are so that's what this pair represents: an object of C and a morphism from F of C to D. Okay, and what are morphisms here? So morphisms here are, so suppose you have two objects, C comma F and C prime comma F prime. So then a morphism is just a good old honest morphism uh, from C to C prime in the category script C, but it should have some property. So it has a property that if you apply capital F to that, then you get this thing on top, capital F of C to capital F of C prime, capital F of H, and that should be compatible with these other morphisms F and F prime, which are both to D. Okay. Okay. So I'll just quickly state what this, I mean, just look at this notation again. So this is F comma D. So the idea is that here you are looking at all objects of C which map to D along with those morphisms. So these are basically all morphisms wherein objects of C are involved with terminating at D. Okay, that's what this category does. So similarly, you can imagine there is a dual category to this. So here the D comes on the other side. So this is D comma F. And this is where things start from D and end with objects in C, from C rather, not in C, but from C. Okay, and then morphisms are again similar, but here you have a dual. So you have things from D and the corresponding thing should commute. So I'll sort of since we spent time on the previous one, I'll not go over this. At any point, if you have questions, please stop me, or if I'm going too fast, please stop me, because yeah, these things are going to show up again and again and again. Okay, so so there's another comma category, and this time instead of an object, you have the entire category D. Okay, so here you basically say that instead of taking a particular object, I take all morphisms which end in which start from sort of images of elements of objects of C, and they terminate in elements, sorry, objects of D, right? So this is pairs, not pairs, triples, F comma C comma D, and now F is a morphism from capital F of C to D. So it starts from something in C or something coming from C, and it ends in something terminating in D. It terminates in D. Okay, and what are the morphisms? Again, they are pairs H1 comma H2, where H1 is from H1 is in C, H2 is in D, and the sort of obvious diagram commutes. Okay, there are things like this. Okay, and then similarly there is a comma category uh, where you have, instead of starting with objects coming from C and ending with objects coming from D, you start with objects coming from D and end with objects coming from C. Okay, and similar morphisms. Okay, so I've not written down what this is, but I hope it's clear. It's a dual notion of this. So these comma categories are very crucial in the study of classifying spaces and sort of dealing with the nitty-gritties of homotopy equivalences and so on. Eventually what we want to do is get long exact sequences and so on. So these are what play crucial roles in theorems governing those things. So they will show up as we go ahead. Okay, so I'll just make a couple of remarks. Again, this will show up later on. So there is a forgetful functor from f comma d to c. So remember, f comma d meant pair c comma little f. So you can just forget that little f and focus your attention on the first component. And then that gives you the forgetful functor, and we have called that j. And morphisms anyway were morphisms in C, so there is nothing really to do there. Similarly, there is a forgetful functor j prime, where now you restrict to the second component for the comma category D comma F. Okay. What about these two other things? Oh, sorry. No, these are still the categories that we had, where little d is an object. So yeah, I should say something here. So if you take this and this, then they have constant functors CD to do so D. So what is this constant functor? So what is CD? That means if you take an object C comma F, you send it to CD sends it to the object D. And if you take a morphism H, it sends it to identity of D. And it's straightforward to check that this is a functor from, so the one I've written is from D comma F. Oh no, the one I have written is F comma D to the category script D. Yeah, so they have these constant functors. Okay, so I've actually said all this. Well, okay. I mean, I've said something more here. Okay, so if you take, I mean, why am I saying this? Why did we define this constant functor? So if we take the forgetful functor f comma d to c and then follow it up with the functor that you originally had, capital F. So this composition of functors, then let's see what this does. This takes c comma f to, first it forgets f, so it takes it to c, and then the functor f takes it to f of c. Yeah, so c comma f goes to f of c. And then what happens to morphisms? So if you have c comma f, h c prime comma f prime, this is your morphism. Then forgetful just forgets the f and f prime, and h was anyway a honest morphism in script c. And then that goes to f of c to f of c prime, f of h. Okay. Okay. So now what we can do is we can define a natural transformation from f compose j to this constant functor d, which is you take eta c comma f to be f, right? So eta c comma f should be uh, a map from f compose j of c comma f, which is f of c, to cd of c, which is d. So it should be a map from uh, f of c to t. And well, there is a map like that, namely f. And then it's clear that the diagrams commute based on how we have defined it. So we have a natural transformation here. And as we know, natural transformations were very crucial in this classifying space business, because when you go to classifying spaces, then we get that BF compose J is homotopic to BCD. But what is CD? CD is just taking, when you go to classifying spaces, uh, this functor will take the entire category, uh, uh, f comma d to the singleton point d, right? So it takes it to the singleton point d. So that means, what that means is that, and this is homotopic to this. So that means that if you follow up these things, so you have bj and then bf, then this is, the composition is homotopic to the constant map, and that means it must factor through the homotopy fiber. Okay, so this factors through the fiber. So of course now I hope, I mean, I don't know. So in point set topology, if we go to the homotopy category, there is a notion of a homotopy fiber. I will define that later on. Okay. Uh, uh, so then, so the point is that there is a continuous function from b f comma d to the homotopy fiber bf inverse of d. And the same thing happens for bd comma f, that also has a map to the homotopy fiber. Okay, so you can see that now if we want to talk about, if you take a functor f and then you take the classifying space and the continuous map induced by that functor bf. So if I want to analyze bf to bd, sorry, bc to bd, then I need to know the homotopy functor. I need to have some control over that in order to write down what happens to the long exact sequence. Okay, and we are seeing that these comma categories, their classifying spaces are, at least they have a map there, and soon under some conditions we'll see that they control how this homotopy fiber behaves. And that means that once we understand the under those conditions, if we understand the comma categories, we should be in a position to understand how the long exact sequences behave. This is really why all this is happening. Okay, so a couple of remarks. Suppose f is a fully faithful functor. Okay, so just recall that fully faithful means that on morphisms, it's a bijection. No, right, yeah. On morphisms, it's a bijection. Uh, so it's bijective on morphisms. So then the comma category, uh, so this is the other comma category, right? So this is script d comma fc. So, and note here that so I think I have not defined this. Right. Yeah, I think this has not been defined. Okay. So my bad. Yeah, sorry. So I should define what this means. I meant here by when I wrote D here, I meant because there's no functor in the picture, right? So I should have some functor. So the functor in the picture here is uh nope. I think okay. So I think I've messed up. Sorry. Let me write this correctly. This should be f of c comma f, and this should be f comma f of c. Right. So so if this happens that it's a fully faithful functor, then if you allow your little d, that object, to be in the image of this functor, so you have f of c here, right? So, sorry. Yeah, you have f of c here in place of little d. So you look at f of c comma f, or you look at f comma f of c, then this has either a terminal or an initial object. So what is the terminal object? Let's say if I take f of c comma f, no, this is not. Okay, no. So for f of c comma f, this is a initial object, and for f comma f of c, it's a terminal object. Okay, so if I have, let me go to the, yeah. So what I'm saying is, if I have, so what are the objects of this? The objects of this were pairs of the form. So I've used c here. So I'll use c prime comma f. And what was the property? The property was that this is um, f of c prime to f of c, right? So this is the collection of objects, right? So I want to claim that, so there is one particular object, namely if I take c comma identity f of c, this object is uh, terminal. Okay, so I should produce maps from unique maps from any c prime comma f to this. So what are those maps? So remember that any such map is a map from c prime to c such that the diagram comes. So I should produce h from c prime to c such that when I apply this, I get that these diagrams, this diagram commutes. So this is identity f of c, and this is little f, and this is f of c, right? So I wanted this diagram, but look at what this is. So this is f of h composed identity f of c. So this is just f of h. So in other words, f of h must be little f. Okay. Now, how do I know such a little h exists? That's why we have assumed that it's fully faithful. So if I know it's fully faithful, then I know such a little h exists. So that's if it's full, it exists. And if it's faithful, we know it is unique. And so there is a unique morphism h such that this happens. So there is a unique morphism h namely that morphism such that f of h is little f, so that c prime comma f maps to c comma identity. Okay, so this shows that this uh, this is a terminal object in this category here. Okay, that's what I was saying on that page. So let me go back. I think I'm here. Yeah. 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 This is what I was saying here. And once I know it has a terminal or an initial object, remember that in the previous talk, we saw that the classifying space is contractible. Yeah. So the classifying space is contractible. So we are going to use this at some point, that if f is fully faithful, then this comma categories of this type are the classifying spaces are contractible. Okay. So already we saw above that classifying spaces have something to do with the homotopy fiber. And now we are seeing that the meaning the classifying space of the comma category has something to do with the homotopy fiber. And now certain classifying spaces of certain comma categories are contractible. So this will be used at some suitable point. We may not actually use all of this. I mean, because this is some of these things are deeply embedded in some proofs, and I may not be able to give all those proofs. I mean, I won't be able to give all those proofs, but these are the kinds of results that I use. So I just want to give you a flavor of that. Okay. Uh, Another thing that we have to note is that if you have, okay, so I think I'm going very slowly. Okay, so if you have u in which is a morphism from D to D prime, then this induces a functor from, which I'm going to call u star, from f comma D to f comma D prime. And so with our usual conventions, I'm putting the star below to say it's quotes covariant. And what is a functor? What does it do on objects? So remember, objects of this are pairs. Objects of this are pairs of this type. So it takes a pair here, C comma F, and it takes it to the pair C comma U composed F. So this is the obvious thing. So here the objects were maps from objects corresponding to objects in C to D, and on this side you have things to D prime. Well, there's a morphism from D to D prime, so you just compose with that, right? That's what this is doing. And similarly, if you have morphisms, so if you have something like this, you just use the same morphism, because remember morphisms were only on the first components. So you use the same morphism. So similarly, if you have D prime comma F and D comma F, then you get a contravariant. It goes in the other direction. So if you have uh, F comma C, then that will go to F composed U comma C, and similarly for the morphisms. Okay. So there is some kind of functoriality here. Only thing is morphisms are inducing functors. Okay, that you have to remember. Okay, so the point here is that you can compare. So remember these are involved in the homotopy fibers, and what this is saying is, if you can compare the objects, you can compare the homotopy fibers. Yeah, or at least things which are have something to do with the homotopy fibers. Okay, so then there is another notion, which is the actual fiber category. So if you have an object of D, so we define the category F inverse D. What is this? So the objects are all those C's such that F of C is equal to D, and morphisms are morphisms F between two such things, such that if you take F of F, then that gives you the identity. Yeah, this is like the obvious thing you could define to be the inverse image, right? So this is a category in its own right. And uh, this, there is a, it has something to do with the category sort of things ending in D. Namely, there is a map. What is a map? You take, it takes the object C to the pair C and then identity of D, identity D. So why does this make sense? Because f of C is equal to D. Yeah, because you started with C on this side in f inverse D. So f inverse D meant f of C is equal to D. So here you can take identity. And morphisms just go to morphisms. There is nothing to do. Same morphism. And similarly, there is a natural functor on the other side. Okay, so there are two definitions here. So if you have a functor like this, it's called pre-fibered. Yeah, pre-fibered. If whenever you take this, it has a right adjoint. Okay, so what is the point? The point is that uh, once it's pre-fibered, which is to say it has a right adjoint. Remember, adjoints give homotopy equivalences. So that means that if you look at the classifying space of this and the classifying space of this, they are homotopy equivalent to each other. They are homotopic to each other. And as a result, uh, any sort of homotopy, sort of any result where you have the classifying space of this guy coming in, if it's pre-fibered, you can just ignore this and look at the classifying space of this and do the same result. And it's called fibered if the same thing happens with the other, on the other side, if comma D, and this has a left adjoint. And again, that means that the classifying spaces of these two are homotopy equivalent to each other. Right. So that's the remark I've made here. Okay. So we are more or less set now to at least state what we are going to need. So there are two theorems. These are both due to Quillen, and these are sort of fundamental in this uh, in any proof that comes in algebraic K theory, which involves Quillen K theory, or the constructions that Quillen has done. The plus construction, the Q construction, S inverse S, etc. So all of them, all the proofs involve these two theorems. And these two theorems, one is called theorem A, and there's another called on the next page called Quillen's theorem B. So I will state them. So what do? Essentially, Quillen's theorem A tells you when this map is a homotopy equivalence. If you take a functor, when does it give you a homotopy equivalence? When you go to the classifying spaces. And what does theorem B do? So theorem B tells you that some certain thing is homotopy Cartesian, but the really key point is that it identifies the homotopy fiber of this map. It identifies the homotopy fiber, which it does this thing, and as a result, it tells you that there's a long exact sequence like this. And what is this thing? These are exactly those comma categories, the classifying spaces of comma categories. Okay, of course there's a hypothesis, so let's go through the theorems now. Okay, but I hope you get an idea of why we were doing the previous stuff. Okay, so here's the statement of Quillen's theorem A. So Quillen's theorem A states that if you have a functor from C to D, and if you take these comma categories and they are all contractible, yeah, the comma categories are all contractible, then this is a homotopy equivalence. Okay, that's the statement. So of course, if you already know homotopy, if you already know theorem B, this is kind of obvious. But this is used in proving theorem B, so we can't use theorem B to and get this as a corollary. Okay, so main point: when is homotopy? When is BF a homotopy equivalence? Namely, if each of these comma categories is a is contractible. Okay, so corollary, if this is pre-fibered or pre-co-fibered, and F inverse D is contractible. So remember that pre-fibered or pre-co-fibered essentially states that F inverse D is homotopy equivalent to the homotopy is homotopy equivalent to these guys, right? So if this is contractible and it's pre-fibered or pre-co-fibered, then this is contractible, and then theorem A applies and says that it's a homotopy equivalence. That's the corollary. So what is the point of the corollary? Often it's easier. This category is much easier to deal with. It's the honest inverse image, and it's easier to deal with. So that's why this corollary. Okay, so this is theorem A. So for theorem B, let's make a couple of comments before going to theorem B. So first of all, there is a natural functor from uh, from yeah from here to here. So what are these categories? So this is a comma category D comma F, right? This is the one that we have looked at. What is this? So you can look at the identity functor from D to D, and you can say, well, I'll replace, instead of looking at C to D, I'll take D to D, and I'd look at the comma category D comma identity D. Now, so what does this involve? This involves um, objects of D, so that this little d has a map to that object. Yeah, that's basically what this category is. Yeah. So if you start with an object in here, so something like f comma c, we know that after applying capital F, D has a map to f of c. Okay, and that map is little f. So capital F of c, excuse me. So capital F of c satisfies this condition that D has a map to it, and so it's in here. So f comma c just goes to f comma f of c. That's the functor. That's the functor on morphisms. On objects, on morphisms, I've written down what it is. It's the obvious thing. H goes to f of h, and so this is the natural functor. Most important, by star. What is star? So star was this comment I made here, that if f is fully faithful, then the comma category has a terminal or initial object. So that was what I called star. And as a result, the classifying space is contractible. Well, here we have the functor identity. Okay, here we have the functor identity. So this is of course fully faithful, right? And as a result, uh, and if you look at D, D is of course in the image of this functor. So that means this is a contractible space. Okay, so we have a natural functor phi from this thing to some contractible space. Okay, so keep that in mind. And yeah, I'll quickly just recall what is a homotopy Cartesian square. So homotopy Cartesian square is essentially, it's a Cartesian square in the homotopy category of topological spaces. So explicitly, one model for this thing is the following topological space. You take triples little x comma gamma comma y, where little x is in this guy, little y is in this guy, and gamma is a path from x to y. Well, of course, that doesn't make sense, but you can apply little f to x and little g to y. So then it's a path from fx to this should be gy. Sorry. Yeah. So these are paths from little f fx to little gy. Okay. So that's a model for the homotopy. Oops. In order to get a homotopy Cartesian square, And of course, I'm saying it's a model because in the homotopy world, everything is up to homotopy equivalence, right? So we don't have, I mean, anything homotopy equivalent to this will also be make this a homotopy Cartesian square. Now, if X is contractible, so that means it has the homotopy type of a point, then this homotopy, uh, then this object here, which is on the top left of the homotopy Cartesian square, is really the homotopy fiber. That's one way of defining the homotopy fiber. And one can formally write down what that means. The point is this homotopy fiber, essentially you can ignore this part here and just look at this. So that gives you a fibration sequence in topology, and as a result you get a long exact sequence of homotopy groups. So that means I get pi n of so if I call this h just for the time being, then I get pi n h to pi n y to pi n z to pi n minus 1 h and so on, right? So you have something like this. This is the right. So from the fibration you get this. That's called the, I think, the Dole-Pupa sequence of homotopy, long exact sequence of homotopy groups. Okay, so just recall this. Sorry. So Quillen's theorem B essentially tells you when you get a homotopy Cartesian square involving BF. Okay, so let's read through it. So if you have a functor like this, such that if you take a morphism in D, any morphism in D, okay, in the category script D. So the induced functor U upper star from these comma between these comma categories, D prime comma F to D comma F is a homotopy equivalence. This happens for all morphisms in D. So then for every D, every object D, if you take this classifying space B of D comma F, it has a natural map to BC. So remember we had this functor J. So I'm calling this JF to keep track that this is about F. So there was a forgetful functor, right? So this forgetful functor induces this map BD comma F to BC. This is the obvious map BF. This thing here is B phi that we defined on the previous page. So D comma F to D comma identity D, there was a functor phi. So this is the classifying sort of the continuous function that one gets out of that. And then this one is, if you have D comma identity D, then again you have a forgetful functor. So you get to BD. Yeah. So uh, you have continuous function like this and continuous functions like this. And what it says is, if this is a homotopy equivalence for all u, then this is a homotopy Cartesian square. Now, note that this is contractible, right? That's what we saw in the previous page, that this is contractible, and as a immediate consequence, you get that this is the homotopy fiber of BC to BD. Yeah. So essentially, Quillen's theorem B is identifying for us, what is the homotopy fiber, provided this hypothesis holds. Okay. So this is crucial to any proof that occurs in K theory, and that's what it does. And as a result, we get a long exact sequence of homotopy groups like this. Okay, where this is the homotopy. This is the comma category, the classifying space of the comma category. Yeah, and you can choose any D. So it's in your interest to choose a D which is which you sort of know how to handle. So in actual situations, you will choose D's where you can sort of, it makes this category easy to deal with. Okay, so I can say only a few brief words. These proofs are highly technical and quite long. So what do the proofs involve? So I can just give some very vague ideas. So first of all, remember there was this other category, comma category, wherein instead of the object little d, you had the entire category script d. I'll recall for you what the objects in this category were. They were triples involving c comma d comma f, where these are objects and f was a morphism from d to f of c. Why from d to f of c? That's because you have this on the left and this on the right. Okay, so I'll just take some water. Yeah. Okay. So now you have triples c comma d comma f. So you can take projections. So we sort of did this trick already for the comma category little d comma f. Now there are two projections for script d comma f. Okay. So I in a hurry I have not drawn this correctly. Right. So there are two projections. One is a projection to the first coordinate, which is the projection to C. The other is a projection to the second coordinate. But now, since the maps are from D to F of C, this will actually go to D opposite. So you have to be careful about the morphism. I didn't write down the morphisms here. If you sort of look at the morphisms and what it does, excuse me, you can check that this actually goes to D opposite. And mm, sort of the point is that you can you can sort of insert this into a picture uh, where the functor f is involved. So that's what I've drawn on the next page. So there is a commutative diagram of functors like this. So this is the thing that I just drew, that you have d comma f, script d comma f. There is a projection to c. There is a projection to d opposite. Similarly, you can take this one, script d comma identity d. Now, if instead of script d you take little d, then this is contractible as a category. But with script d, it's not. It's in fact a fairly involved category. And well, you can sort of check that even by hand that it's homotopy equivalent to d. So the main sort of punchline of the proof is that, so I want to check that this is under some conditions. I want to check that this is a homotopy equivalence. That's what theorem A says. Okay, so theorem A told us that under certain conditions on the comma categories, namely they were contractible. Under those conditions, this is a homotopy equivalence. Now, the sort of main sort of punchline of the proof is to show that this is a homotopy equivalence. This is a homotopy equivalence. And then this is a homotopy equivalence on the same lines, because for this, we already know that the comma categories are contractible because they have terminal and initial objects, etc. And so that, I mean, so these two will also be homotopy equivalences. And then to show this is a homotopy equivalence, note that this is a homotopy equivalence and this is one. So it's enough to show this is a homotopy equivalence. But now if I show this is a homotopy equivalence and this is a homotopy equivalence, then well, this is equality. So this must be a homotopy equivalence. So this must be a homotopy. This is kind of the idea of the proof. So the punchline is to show this P1 and P2 are homotopy equivalences when the comma categories are contractible. And that's kind of a hard proof. It's a 4-5 page proof. And the key sort of idea is to construct something in the middle, which is a bisimplicial set. And you will see sets of that kind when you do Waldhausen, this W construction. So they will show up naturally in that context. So you have to use that kind of. So it was already Quillen had this idea of using this bisimplicial sets, and that was sort of taken to its natural sort of conclusion by Waldhausen in a sort of more deeper context. Okay, so I can't really get into this at all. It's real. In fact, I don't even sort of completely understand that proof. It's fairly involved. Okay, so for theorem B, what do we do? So the first thing we can do is uh, see we can so checking that this is a homotopy equivalence is not. I mean this doesn't require the hypothesis. It's really this that requires the hypothesis. Okay, so I can replace this guy and this guy. So this is the Cartesian square, and I want to show it's a homotopy Cartesian square. That's the point. So I can replace this and this by B of this and B of this. Okay, so it's enough to show that this is a homotopy Cartesian square. Now there are natural functors here. So these functors are kind of natural, and again that that's some involved use of bisimplicial sets. And this is, I mean, once you know theorem A, this is not that hard. But again, it uses bisimplicial sets and crucially uses theorem A. Okay, so it involves this this picture. Okay, so that's sort of what goes into the checking for the proofs of these theorems. Okay, so now with all this background about classifying spaces and Quillen's theorem A and B, let's get back to symmetric monoidal categories, which is what we started with. Okay, so for that we'll need some topological construction called H spaces. So so I'll just define that quickly. So a pointed space is called an H space if you have a continuous function of pointed spaces x comma x to x such that when you take this map x going to x comma x naught and then applying this is called mu. So this mu is supposed to sort of represent some kind of it's like the tensor when we did the symmetric monoidal categories. Yeah, some kind of product on this space. So when you do x goes to x comma x naught and then apply mu, then or you do it the other way by putting it in the second coordinate, either the first coordinate or the second coordinate, then these are both homotopic to the identity map on x comma x naught. So what this is saying is if you take this thing by just the identity x goes to x, right? So then this is like x comma x naught is going to some kind of product and x naught is like your identity. So it goes back to x. So so this thing is homotopic to the identity map, and so is this thing. It's homotopic to the identity map. That's the data of an H space. Now it turns out that for an H space, you can always replace mu. So remember, mu is something like this along with this data. You can replace it by mu prime, so that if you take mu prime of x comma x naught and mu prime of x naught comma x, it's actually equal to x. Okay, so this is actually like x naught is playing the role of identity. Yeah, so whenever mu exists, you can show that mu prime exists. So you from now on we'll just assume that an H space is this along with the data that mu of x comma x naught is equal to x and mu of x naught comma x is equal to x. Okay, what are examples? So topological groups, then the spheres S1, S3 and S7. So this is some related to some famous result of Adams. These are the only H spaces amongst the spheres. And then CP infinity via polynomial multiplication. I don't have time to show how this goes, but this is very algebraic. And finally, this is really the um main example, the loop space. Yeah, the pointed loop space. So what are the elements of this? They are loops at x naught. And if you have seen the construction of pi1, the fundamental group, I'm sure all of you have, then when you check that pi1 is indeed uh, a group, essentially what you are checking is that the loop space is an H space. That's what the proofs go through. Okay, so so the operation is concatenation, and I'll sort of leave you to figure out that. So if you remember how you got pi1 is pi1 of x naught is a group, that is exactly saying that omega x naught is an H space. Okay, so some definitions. So an H space is homotopy associative if sort of the obvious diagrams commute, namely if you take mu cross identity and identity cross mu, then and then mu again, then these things commute. Of course, commute up to homotopy, right? So all of these are homotopic, meaning sorry, all of these pictures commute up to homotopy. And it's called an H group if further there is an inverse. So an inverse is this data. So I'll skip what this picture is doing. Essentially, it's like saying you embed this via the diagonal map, then take x comma x to x comma j of x. J of x is like its inverse. And then when you apply mu, it goes to x naught. So that's saying that if you take this x naught, then this is homotopic. The same thing if you do instead of 1 comma j, 1 cross j, you do j cross 1. Yeah. So that's what this data is. And we say it's commutative if you take the switch map x comma y to y comma x, then these are homotopic. Okay. So that's the data of a homotopy commutative uh, uh, of an yeah. So we have homotopy, we have an H space, we have an associative H space, we have a H group, and then we have an commutative H group, sometimes H commutative H group. Fine. So how is this related to symmetric monoidal categories? So if you have a symmetric monoidal category S, then its classifying space is homotopy commutative, homotopy associative H space. Okay. So if you, I mean, this is kind of a direct check. There is nothing really to do here. The map mu is induced from the tensor, and remember what does this mu do? Mu applies only on objects, right? On points. It's not saying anything about the other structure. It only says there's a continuous function, and you have to only talk about points. So points in BS are just the objects of S. So it's like you have an operation on the objects of S, which you do. That's the tensor operation. So from there, if you assume that it's a symmetric monoidal category, it's homotopy, commutative, homotopy associative. Yeah, that's straightforward. Okay. And now if you go to S inverse S, then not only is it homotopy, commutative, homotopy associative, H space, but it's actually an H group. And here you need an inverse. So we have already seen what the inverse is. If you take m comma n, then the inverse is n comma m. And then it's a check that indeed all those pictures commute. I'll suggest you, if you want to understand this well, then you do that checking. And of course, if you have a I didn't say what are H-space morphisms, but I think it's clear what those morphisms should be. So if you take BS to be S inverse S, then this is an H-space morphism. So an H-space map. Okay. So now, if you have a map of H spaces X to Y, then this is called a group completion. Yeah, it's called a group completion. If Y is an H group and the induced map pi naught X to pi naught Y is the group completion for monoids. So remember, this is an H space. That means X has some operation. So in particular, it's like a monoid. So pi naught X will become a monoid. And if Y is an H group, then pi naught Y will become an actual group. And then we are demanding that this is the group completion, the Grothendieck group construction. And finally, and this is really the key to the definition, there is an operation of pi naught x on HIs, the homology groups. And so if you sort of invert this, then that gives you an isomorphism between the homology groups. Okay. So first of all, group completions are unique up to homotopy. It's not clear they exist, but if they do exist, then they are unique up to homotopy equivalence in the category of CW complexes. And you can kind of read off why, because you see, you will be able to get, so you will have a map X to Y and X to Y prime. So suppose you have two group completions, and based on the data that it's an H group, it will give you a continuous map from Y to Y prime and the other way. And then because of this data, it will give you that HIY to HIY prime is a isomorphism, and same thing the other way. So that means you have maps from Y to Y prime which induce isomorphisms on homology groups. But now both of these are CW complexes, and so the Whitehead lemma applies, and that will tell you that Y to Y prime is actually a homotopy equivalence. So these are unique. So the sort of punchline of the S inverse S construction is that this is a group completion. Okay, this map is a group completion. So it satisfies all these three properties. So we have already seen that pi naught of BS is S inverse S is an H group. We have seen it's a group. Sorry. We have seen BS inverse S is an H group. That was this comment here. That's straightforward, as I said. We have seen the induced map is the group completion. That was a lemma that we proved earlier. So what we need to see is this third part. Now, this is a really involved proof, and it involves some construction beyond just S inverse S. Namely, we have to give. So I stated this earlier that we have to give an idea of how S acts on any category C. Okay, and then we have to construct S inverse C, and then from there we have to use this Quillen's theorems A and B and show that. Okay, so the proof is involved. So I will of course not give the entire proof, but I'll at least give an idea of what is involved in this construction of S inverse C. So Dipankar, it's 4:29.
Yeah.
So should we
Can you wrap up
stop
in 5 minutes?
I think I can wrap up at least this part in 5 minutes. I think
Yeah.
that we started a little late because of that.
Yeah, sure. Go ahead. Yeah.
So maybe 5 minutes. I'll just say how S inverse C is constructed. I don't know if that will be going to be fast. And then this idea of acting invertibly, and then its relation with what has happened before. Okay, so now suppose we have a category C on which S acts. So what that means is you have a functor S cross C to C, and it will involve various diagrams commuting. So remember that when we said S is symmetric monoidal, there were a bunch of things that we said happened. So there was associativity, the left uniter, the right uniter, and they involved various triangle. There was a triangular law and a pentagonal law, etc. So all of those things have to come in here. Okay. So it's a functor which all those relevant diagrams, all of them commute. Whatever makes sense commutes. Okay. So I've not written this down. Then we can construct this category S comma C. For whatever reason, it's been called the inner product of S comma C. So what is this? The objects are the same as the objects of C, and the morphisms have the following description. This is on the lines of how we constructed S inverses. Okay, so it's not too hard to understand. So here you have two objects of C. So then you have to construct a pair. You have to consider a pair S comma F, and the so what does this do? It gives you mean F is a morphism from S tensor M to N. Okay, that's what this data is. And two such things are equivalent if there is a isomorphism from S to S prime, which makes this diagram commute. Okay, so this is very similar to what we saw when we constructed S inverses. Okay, so uh, that's the category S comma C. And then you define S inverse C to be the following category. You take the inner product category of S comma S cross C. Okay. So remember when we did S inverse S, you first took S cross S and then you took some kind of action of S on S cross S. Okay. So we are doing exactly the same thing here. So this is inner product of S comma S cross C. So what that means is you take pairs like this, and then the morphisms will be like S comma F1 comma F2. This is exactly what the data was for S inverse C. Okay. So that's what this is. Of course, what is the action here? The action is the diagonal action, uh, which means S tensored with. So the action is M comma C goes to S tensor M comma S tensor C. Okay, and these tensors are different tensors. They are the tensor. This is the tensor in the symmetric monoidal. This is the tensor that was up above here. This one. I mean, I didn't call it tensor, but I'm using tensor for that. Okay, so that's the definition. The definition is of S inverse C. And if you replace C by S, then S inverse S is exactly S comma S cross S. Okay, so this is not some new thing. We have basically done this before. Only thing is you can do this for any category. And we'll say that S acts invertibly on C if the functor induced by each S induces a homotopy equivalence. Again, this is an idea we have seen before. This was the idea of why we went to S inverse S in the first place. So we saw that S acts invertibly on S itself. Yeah, that we saw. So my bad. We saw that S acts invertibly on S inverses. Right? That's why we constructed S inverses. Okay, so now as in the previous thing where we had various actions on S inverse S, remember we had these G1 and G2 and so on. So here also we can play that same game. We can do something like G1 and G2. So one is putting things on the right, the other is putting things on the left. Okay, and then for the same reason that we had for S inverse S, we have a natural transformation, and that will make these two things, RS and LS, acting on the right and left, they will be homotopy equivalent. Okay, so S inverse C is genuinely something where S acts invertibly. That's the point. the same idea. Okay, so I'll skip this proof. I actually wanted to give this proof. So if S is consists only of isomorphisms, then this category is actually contractible. Okay, and this is key to what happens next, because so I'll just stop with this page. So if S is a symmetric monoidal category with S consists of isomorphisms and the actions are faithful, so this is some extra thing you need. Then if S acts on C, then it acts invertibly on C if and only if this is a homotopy equivalence. Okay, that's the statement. Okay, so the idea, this is a fairly involved proof, and the main point is that you can get something like this, which is a homotopy fibration. This is, as you can see, this is something, it will involve Quillen's theorems A and B. And then once you get this, note that we stated this was contractible. I didn't prove it, no time. So if it's contractible, then you can really get rid of this and say this is a homotopy equivalence. That's what this statement says. Okay, this is the idea of the proof. Okay, so again, so the final punchline is, using this, you can say that this is the third thing that we wanted to prove group completion, that this is an isomorphism. So this is true for any C actually. Yeah, and then you just replace C by S and you get that theorem. Okay, so I'll stop here. Yeah.
All right. Are there any questions?
Yeah, this is kind of fast, so I apologize for that.
All right, then if there are no questions, then let's stop here.
Okay, thanks. Yeah, it looks like I may need another talk. We'll
Okay.
discuss that later. Yeah.